Okay, so what I'm planning to do today is I'm going to try to show you using these cards here kind of how some of these different sorting algorithms that we've talked about, how they might be done in a real world environment like with the cards. That way you can kind of understand maybe in a physical example how this would work. So you're going to see here there's 5. So we talked about 4 in class. I'm going to go ahead and give another set here for another type of n squared algorithm that we didn't talk about in class. It's called selection sort. But I thought it was interesting because a lot of these are ways that we might sort things in real life, and that's why these algorithms exist in computing, is because a lot of them were based on how people might sort real world group of objects. It's how I might sort, again, your quizzes or your exam papers if I had them. I decided not to do quizzes or exam papers. I didn't want to show those on a video. Don't want to make anybody feel sad or maybe happy. Maybe, oh, I'm better than everybody else or something like that. So anyway, so what I want to do is I'm going to take each of these are random. They're random, but they're the same random order. So all 5 of them start off with the same numbers in the same order. I did them by suit so that we could maybe see this a little bit easier. Okay, so what we're going to do is we're going to show you how first insertion sort would look with a deck of cards. Okay, so what we would do is we would take this deck of cards and we would say, remember, insertion sort is we want to take the lowest card, we want to take the lowest value, and we want to put it into the first position and move everything else forward. Okay, so we're going to look for the lowest. Now, we're going to hold on to anything that's the lowest so far. So right now, as we start, 10 is the lowest. Then we come to here and we say, oh, ace is now the lowest. Okay, we're going to do, by the way, ace is going to be 1, then we're going to go up to 10, then jack, queen, king. Okay, all right, so ace would be the lowest. Okay, so if we put this down, so ace is the lowest, so we're going to hold, we're going to say that's the lowest. Is there a lower? 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 There's not until we get to the end. So what do? We take ace, we put it forward, and we move 10 back. Now, in a hand of cards like this, this is easy, right? The reason why this is easy is because moving things forward doesn't really require anything. It just kind of requires to push this forward, and it's done. It moves into those positions. In an array, this would be a lot harder because in order to move 10 into that position, we'd actually have to physically move it. Well, not physically. We'd have to digitally move it into that next position. Okay. So now that we have the lowest card in the first position, we don't have to look at that card anymore, right? We can put it down on the table. Okay. So now we're going to look for the next lowest. Now, one of the problems here is that in our human mind, you would probably say, well, 2 is the next lowest because I've already looked through all these cards once before and seen that 2 was the lowest. The problem is that in a computing system right now, in a simple sorting algorithm, we can't do that. We can't remember things about the cards from before. So we're going to look. Okay, 2 was the lowest. I'm going to move it down. Okay, we're going to look again. Look, okay, 10 starts out as the lowest, 5 is lower, 3 is lower, nothing else is lower than 3. We move it into that next position and we push everything else back. Okay, next 10, 5 is lower, nope. Okay, 4 is lower than 5. Okay, so we push that into the first position. Okay, 5 is the lowest. Okay. 10, 7 is lower. Okay, now 6 is lower. Okay, so 6 gets pushed to the front. And then we just keep doing this, right? So then we look through again. 7 is the lowest. 7 stays the lowest, so it gets moved to the front. 10. 8 is lower than 10. And then that stays. Okay. 10. 9 is lower than 10. So 9 gets moved. 10. We look at the rest. Nope. Queen is the lowest. King is not lower than queen. Jack is though. Boom. Queen is the lowest. King is not. Okay. And now we have a sorted array, a sorted set of cards. Okay. That's one. All right. The other one that we talked about, the other big O of the n squared algorithm we talked about in class was the bubble sort. The bubble sort is going to be a little bit harder in this. So the way that it was described in class was bubbling the biggest card. If two things were bigger, we swapped it so that it would go to the back. So the biggest card would end up in the back position. Okay, I'm going to do it a little bit different. In that I'm going to do the same thing as I did here. I'm going to keep moving the smallest card forward. So what that means is that instead of looking at the first card and moving to the back to find the smallest card, what we're going to do is we're going to look at the back and come forward. Okay? So 4 is smaller than 9, so we're going to swap them. Okay? 4 is smaller than Jack, so we're going to swap them. 4 is smaller than King, so we're going to swap them. 4 is smaller than 6. 4 is smaller than 8. 4 is smaller than Queen. 4 is smaller than 7. 4 is not smaller than 3, so we're going to leave the rest of this alone. 3 is smaller than 5. 3 is not smaller than 2. 2 is not smaller than ace. Ace is smaller than 10, so this is the way that we end up at this point, okay? So we bubbled it up to the front, okay? Now we don't have to look at that one anymore. So now we start at the back again. So 9 is smaller than Jack. 9 is smaller than King. 9 is not smaller than 6, so we leave it. 6 is smaller than 8. 6 is smaller than Queen. 6 is smaller than 7. 6 is not smaller than 4. 4 is smaller than 5. 4 is not smaller than 3. 3 is not smaller than 2. 2 is smaller than 10. Okay. Keep going. Jack is smaller than King. 9 is not smaller than 8. One of the things that you might be noticing through this is also through some of this is as we move these things forward, some of these numbers that were before, that were out of order before, even though we didn't push them, bubble them all the way to the front, we still kind of have more general ordering going on. So there's going to be less swapping later than there was before, right? So, like some of these that were out of order before are now in order, right? Okay. So we're getting a trend here. All right, let's see. Where were we? 9 is not smaller than 8. 8 is smaller than Queen, but it's not smaller than 7 or 7 is not smaller than 6. 6 is not smaller than 5. 5 is not smaller than 4. Notice that we're not doing any swaps here along this whole route here. Okay? But we still have to swap here at the end, right? Because 3 is smaller than 10. Okay? And notice that fewer swaps are going to be happening like through this whole section here as we pass through this section. If we find a number that is smaller than this out here, we would do a lot of swaps. But once if all that's past the 8 is all bigger than 8 throughout this whole section, no swaps. Okay? So let's start back at the back. King, nope, we don't swap with Jack. We don't swap with 9, but we do swap with Queen. Okay? We don't swap with 8. 8 doesn't swap with 7. 7 doesn't swap with 6. 6 doesn't swap with 5. 5 doesn't swap with 4. 4 does swap with 10. Okay? King doesn't swap with Jack, but Jack does swap with Queen. All right? 9, 8, 7, 6, 5 swaps with 10. So now notice what we have here. We have, outside of this first card here, we have a completely sorted list, right? It's a completely sorted array, right? But we don't know that. We can look at this and know that. Our computer cannot, so our computer still has to go through them one by one. But for the sake of time, you'll realize that there won't be any swaps until we get to this, but then suddenly, what? 6 will swap with 10. and then we'll get to the whole thing, and then 7 will swap with 10. Get through this whole thing, and then 8 will swap with 10. Get through this whole thing, and then 9 will swap through 10. Okay? And then in the bubble sort implementation that you have available on the lecture examples, it would now look through this and see that this is a sorted array and be done. The traditional bubble sort would still look, and we're done. We now have a sorted stack of cards. Okay. One of the reasons I want to go ahead and do the selection sort too. So all my big O of n squared is all going to be the red cards, by the way. Okay. The reason I want to do the selection sort is because insertion sort would be maybe how you might actually do that in a real hand of cards kind of situation, because it's easy to move them forward. Selection sort's actually a little, it's similar to insertion sort. It's just you swap, instead of whenever we find the smallest card in here, instead of just putting it into the front and moving everything else back, it just swaps it with the front card. Okay, so even though both selection sort and insertion sort are both considered big O of n squared algorithms, selection sort can be faster because it doesn't require a lot of moves of the array from one position to another. Although insertion sort could be much faster with a data structure where inserting is faster. And I hope you remember from our discussion on data structures that linked lists, inserting is very fast, right? Finding is slow, inserting is fast. All right, so a linked list for an insertion sort would probably be it could be a good option. All right, so again, we look through and we find the smallest one, and we swap it with the first card. Okay, then we look through and we find the smallest one, which would be this, right? And we swap it with what is now the first card in our subset. So it would, in this case, it would actually be the second card. We swap it with the second card, right? But because I keep putting these down, we're just going to be swapping it with the first card in the subset, in the remainder of the array. Okay. And we look for the smallest, which will be 3. Okay. And then we don't insert. What we do is selection sort swaps these two cards. Okay. Harder to do with cards or with a stack of papers or something like that, but easier for the computer to swap instead of having to move everything forward. Okay. So now we look for the next smallest one, the 4, and we swap it with the front card. Okay. We look for the next smallest one, the 5, and we swap it with the front card. Now you'll probably notice that in this last time just now, the selection sort, because 4 and 5 are right next to each other, the selection sort actually acted a little bit slower because there was multiple swaps, whereas with insertion sort, 5 would have already been in position. That happens. This is why we do average case analysis and not best case analysis for our understanding of algorithms. Okay, let's see. We look for the lowest one again. I actually forgot where I am, what number I'm on, so I'm going to actually have to do this. So 7 is lowest so far. Okay, so 6 is lower than 7, and we're done. Okay, so 6 swaps with 7. Okay. 7 is the lowest. Okay, it's going to stay there. So 7 swaps with queen. Okay. Oh, 8 is the lowest. So we just leave it there. It swaps with itself. We just leave it there. Okay. Queen, king, jack is lower. 9 is lower. Okay, so 9 is the lowest. We're going to swap that with the queen. 10 is the lowest. We're going to swap that with the king. Okay. Jack stays where it is. Queen stays where it is. King stays where it is. All right. So those are our big O of n squared algorithms. Oh, we still got 2 more, right? We still got 2 more to do. All right. So for a large stack of papers, so quiz papers or a whole deck of cards, these would be very time consuming, right? For a simple stack like this of 13 cards, or even if you were just playing like a hand of cards, like if any of you guys play poker or spades or hearts or something like that. There's also a Turkish game I've never played. I want to learn it. But if you have like just a hand of cards, sorting those using one of these methods, fast, not a problem, right? But when we start getting into larger stacks, we're going to see that some of these other algorithms are much faster. Okay, so the first one we talked about was the merge sort. Now what the merge sort does is we divide it into two stacks, right? So 1, 2, 3, 4, 5, 6, 7. So it's going to be 7 cards and 6 cards, right? And then we're going to take the 7 and we're going to divide it into a stack of 4 and 3. Okay? Let me move some of this out of the way because it's going to start getting. Okay? And then we take the 4 and we divide it into a stack of 2 and 2. Okay? And then what we're going to end up with is each of these is going to be a stack of 1 and 1. And what we're going to do is we're going to sort them, right? We're going to merge them. So it's going to be 1 and 1, and we're just going to merge them back together into a sorted order. Okay? 1 and 1, and we're going to merge them back together into a sorted order. Okay? And then we will merge these two. Okay, we take up the ace, we take up the 2, put those together. We take up the 5, and we take up the 10. Okay, so now this is a sorted 4-card array. Now here we take the top 2, it's a 2 and 1, so this is already sorted. So then this comes to 1 and 1, we put them together, then we merge these two together. We take up the 3, we take up the 7, we take up the queen, and now we have a sorted array there. Okay, and then we just merge these two together. So now we get ace, which is less 2 or 3, which is less 3 or 5, which is less 5 or 7, which is less 10 or 7, which is less 10 or queen, 10. Queen doesn't have anything else left, so there you go. Now we're done. Okay. Oh, wait, we still have these other 6 over here to do, right? Okay. So we just divide these into 3 and 3. Divide this into 2 and 1. Divide this, right, to 1 and 1. 6 becomes 8, 8's friend. King goes on the back. Done. This gets its own. These two become like that. And now watch. Okay, now I want you to see this one because it's probably the best example we're going to see today on this. Here's array 1, here's array 2, and I want to merge them together. Now, when I take this one up, there's no array 2 anymore, right? And so I don't have to do this whole compare 9 versus 4, 9 versus something, jack versus something. I can just take up the rest of the array and put it to the back, okay? And the reason why we can do that is because this doesn't have anything to compare to. It's not going to be greater than anything, less than anything over here because there's nothing left over here, all right? I've already hit the max value over here. So I just pick them all up. This is what those 2 extra while loops at the end of the merge routine do. Is they just say, take up the rest of whatever array is left and put it to the back of my merged array. Okay, so here we pick up 4, we pick up 6, we pick up 8, we pick up 9, we pick up jack, and we pick up king. Now we have 2 stacks. We pick up ace, we pick up 2, we pick up 3, we pick up 4, we pick up 5, we pick up 6, we pick up 7, 8, 9, 10, jack, queen, because it's less than king, and now we don't have anything left over here. We just pick up the rest of this one. Okay? All right. Okay, so the last one's going to be a bit difficult in terms of doing it with cards, because even though it's very good, it's quick sort, it's very fast in computers, it's going to be kind of weird to do it with cards, I think. But let's have a go and see what happens. All right. All right. So first things first, we pick a pivot. So what we're going to do is we're going to take this, okay? And basically what the point of this is everything less than this is going to go to the left. Everything greater than this is going to go to the right, okay? Now the way that the quick sort routine does this involves like moving all this stuff throughout the array. I'm just going to do this a simple way of saying less than 10 goes to the left. I'm just going to do it like this. Greater than 10 goes to the right. Okay? So now what I'm going to do is I'm going to go to the right here again. I'm going to do this again. Okay, so now I have a new pivot for everything greater goes to the right. Everything less goes to the left. Okay. And then I'm going to do that again with this. Now, this might be our pivot, then these would go to the right, and then this would be our pivot, and this would go to the right, and now we have a sorted array here. Okay. So now we have a sorted array here. We take this up, and we'll put it to the back. Okay. Now, bad pivot, right? That's a bad pivot because everything's just going to go to the right on that. Okay. Much better pivot. All right. Okay. Much better pivot. To the right, to the left, to the right. Okay. So now when we put them back together, so this we will sort these two like that. So now when we put them back together, 7 was there, 6 was there. This was our pivot here, right? Now remember, this is the sorted right array of this pivot, and this is the sorted left array. Now notice if we've done this right, then these are all in position already, right? So we can just pick them up like that. So now we have a sorted left array, a pivot, and a right array. And we just do this again with this side. All right. Pivot is the jack, which means these two go to the right. Pivot's the king, which means this goes to the left. So now this goes here. This goes here. All right. And now we have a sorted left array, a pivot, and a sorted right array. And if we just pick them up, and there we are, right? Okay, so that's how quicksort would work. Again, I'm not sure some of these n-log n algorithms, how well they work in real life. Good question. And like I said, for different size data sets, some of those n-squared algorithms could be potentially faster for very small data sets. The whole reason of why we do algorithm analysis like this is not so that we can figure out what necessarily is the fastest algorithm for a particular data set. We want to know what's the fastest algorithm in general, and especially as amounts of data points get larger and larger. We want to make sure we cover all that. All right. So I hope that was helpful. I think it's helpful to me to be able to see these things in practice and visualize them. But other than that, I think this will be the last lecture video I post of any kind. The next time you see me, I do plan to do some type of review type thing like I would for a final exam, but I may just record that and post that. We may do a live meeting, but I may just record it. I haven't decided yet. All right. Have a good Bayram tomorrow on Dokuz Mayas. And yeah, so iyi tatiller. All right. Have a good afternoon.